Next speaker will be speaking on the impact of control theory and cybernetics on Maxwell's paper on governors. The speaker is Professor Rodolphe Sepulchre, Professor of Engineering, University of Cambridge. Let's welcome Rodolphe.
Good afternoon. I would like to start this talk with a quote, not from Maxwell, but about Maxwell. And the quote is by Norbert Wiener, who published in 1948 the very famous book called Cybernetics. And he wrote the following: "We have decided to call the entire field of control and communication theory, whether in the machine or in the animal, by the name cybernetics, which we formed from the Greek Kubernetes, or steersman. In choosing this term, we wish to recognize that the first significant paper on feedback mechanism is an article on governors, which was published by Clerk Maxwell in 1868, and that governor is derived from a Latin corruption of Kubernetes." So since then, control theorists like to think themselves part of the noble heritage of Maxwell. And I probably owe to that very quote the privilege of being here today. Now, from the viewpoint of history, if you trust someone like Otto Mayor, who used to be a curator at the Washington Museum of Science, between Maxwell and Wiener, that paper was never cited, or maybe only once. And maybe that was not the best paper by Maxwell. In any case, I think many physicists still today would question why Maxwell got distracted by such a futile subject as governors for many years while working on the Maxwell's equation. So for that reason, I'll divide my talk in two parts. In the first part, I will sort of... Should I stand here? Oh, sorry. So in the first part, I will sort of summarize what was in that famous or infamous paper on governors. And then in the second part, I will perhaps comment on why, as a control theorist, I still feel like we deserve the paternity of Maxwell. Governors, so maybe some people in the audience wonder what a governor was at the time of Maxwell. So governors had been made popular mostly by Watt about a century earlier, because when Watt improved the design of this steam engine, he needed a speed regulation device. So you can really think of the governor as the ancestor of the speed regulation device that we now have in our cars. And so Watt needed a device to prevent the wheel to speed up too much. And he came up with this very clever device that today we call a Watt governor that works as follows. You mount these two flying balls on the axis of the wheel that you want to regulate. And of course, if the speed increases too much, the fly balls will move upwards. And then when under centrifugal acceleration, and then when the balls move upwards, they will eventually close the valve that lets the steam come into the engine. And therefore, the torque engine will be decreased. And that is essentially a feedback mechanism that if the speed increases too much, the motor torque is reduced. And if the speed decreases, the motor torque is increased. And in this way, you try to regulate the speed. Okay, this is the version of the governor that I'm using in my classroom to teach the very first lesson about feedback. And so you see, we still have the speed sensor invented by Watt. The steam engine is replaced by this electrical motor. But most importantly, the complicated mechanical device that connects the sensor to the actuator is replaced by one line of code. And that line of code is essentially the gain of that feedback mechanism. that was quite difficult to tune at the time of what? Because if you make it too stiff, then you create oscillations. And instead of regulating the speed, you will keep oscillating, so you will sort of overreact. And if the gain is too weak, then the whole speed regulation device is very sluggish, and you don't have a good regulation. And so for that reason, the art of designing governors became sort of a fashion in the 19th century. And many very famous people contributed to the design of some form of governors. But as it's quoted, most of those governors were afflicted by problems of inaccuracy and instability. You see always the same trade-off that seemed to foil the efforts of both theory and practice. So that is the reason, perhaps, why governors were somewhat popular or fashionable in the time of Maxwell. But there is at least one more reason why Maxwell became interested in that device, is that, yeah, by the way, Otto Mayor, after writing the historical paper about Maxwell's paper, became so interested in the topic that he called this a social phenomenon of the 19th century, that among its participants, so those people interested in speed regulation, we find not only countless engineers, whose names are now forgotten, but also illustrious physical scientists like Airy, Foucault, Kelvin, Maxwell, and Gibbs, men whom one would have expected to incline towards the pure side of science. As I said, there is at least one more reason why Maxwell became interested in the governor, is that he was part of a committee in 1861 responsible for establishing some electrical standards, and that committee devised an experiment to measure the resistance of a circular coil. And in order to extract the measure of the resistance from that experiment, the speed of the coil had to be known and had to be regulated closely. And so the committee decided to use a governor to achieve that speed regulation problem, and they borrowed a governor which had been made by one of its members, Henry Charles Freeman Jenkins, professor at this university. And that is the governor that attracted the attention of Maxwell. So this is the very governor that was used by the committee. I was hoping to find this governor in Cambridge Science Museum, but couldn't find it. But I was told that I should probably go to, that it probably still exists somewhere. Anyway, you see that this device is slightly more complicated than Watt's device. Perhaps I'll come back to that later. And apparently there is significant evidence that Maxwell became very interested in the way that device was working or not working. So that's what eventually motivated this paper, you see, 7 years later on governors. And there are essentially two types of contribution in that paper. The first thing is that he wants to reduce these design problems to a stability question that connects to his earlier work, as I'm going to say. And then he's introducing in that paper, perhaps for the first time, a distinction that has become quite fundamental in control between what control theories call proportional and integral control. So about the first part, here is how Maxwell starts the paper. I propose at present, without entering into any details of mechanism, to direct the attention of engineers and mathematicians to the dynamical theory of such governors. So the paper is really about converting this question of why the performance of those devices is perhaps poor into a stability question. And in particular, he's talking about the fact that the device could produce damped oscillation, the actual motions corresponding to these impossible routes, impossible was the name for complex routes at the time, are not generally taken notice by the inventors of such machine. So essentially, he's turning the analysis of a governor into the stability analysis of what we call the linearized system, which amounts to decide where the roots of a certain polynomial are located. And of course, this connects the study of governors to very important tradition on stability and studying stability through linearization. Linearization, of course, was known since Newton, but the real interest for stability, which is about the asymptotic motion asymptotic questions of motion, became a central focus only in the 19th century under the influence of people like Legendre and Laplace. And then Maxwell's paper analyzes the stability of governors through linearization. And that is sort of a breakthrough because at the time, the dominant approach to study stability was based on energy considerations. And in fact, Airy himself had tried to study the stabilities of governors in 1840, but with not much success based on these energy considerations. And that perhaps explains why you've seen this morning the very enthusiastic comment of Airy about Maxwell's paper on the Adams prize, because Airy was very impressed that chief linearization was solving a problem that he hadn't been able to solve himself earlier. And of course, this is, for Maxwell, going from the stability of Saturn rings to the stability of governors was essentially the same question. So he applied exactly the technique that had been successful in his earlier work on Saturn rings, where we heard about this morning. And this is a quote from that very memoir that he considered to show the importance that he attached to stability. This is a very general and very important problem in dynamics. It is this: having found a particular solution, to determine whether a slight disturbance would cause a small periodic variation or a total derangement of the motion. Okay? And so this is quite remarkable because after Maxwell's paper, about 10 years later, eventually the Mathieu theory came with the work of Lyapunov, who sort of combined energy stability analysis with Lyapunov functions, which are sort of energy functions, together with the analysis based on linearization. Now, there is an interesting question that because he's reducing the study of stability to computing the roots, or not computing, but deciding whether the roots of a certain polynomials have a negative real part, he's saying that all the possible roots, and all the possible parts of the impossible roots, or we would read it today, the real parts of the complex roots of a certain equation shall be negative. I have not been able to completely to determine those conditions for equation of a higher degree than the third, but I hope that the subject will obtain the attention of mathematicians. And eventually, about 10 years later, the general solution of that question was provided by Edward Roth. Now, there is an interesting connection between Ruth and Maxwell. That lasted over many years. First of all, they both graduated from Peterhouse in the same year. Ruth as a senior wrangler, Maxwell with the second place. So the story started bad way for Maxwell. But then a few years later, Maxwell won the 1858 Adams Prize for his memoir on stability of Saturn rings, as we heard this morning. Then eventually, in 1871, Maxwell became a professor in Cambridge, while Ruth never became a professor, but made a very successful career, apparently, of supervising math students. And it's very clear that it is through this supervision that he heard of Maxwell's interest for solving this particular mathematical question. And eventually, Ruth won so 20 years after Maxwell, won the same Adams Prize for his memoir on the criterion of dynamic stability. Maxwell was a member of the prize committee. And probably that the paper of Ruth is the only citation of Maxwell's paper until the work of Wiener, 60 years later. Okay, so the second part, or the second contribution of that paper is to establish this classification between governors that achieve proportional versus integral control. The writing is quite obscure, but the idea is the following, is that Maxwell doesn't want to call the Watts regulator a real governor. He would just call it a simple moderator. And that's because Watts governor is just what we call proportional feedback. So the corrective action is proportional to the error of regulation, which means that with proportional feedback, you never achieve exact regulation. You need an error, and then you can make a correction proportional to the error. Okay? And then, of course, the question arises whether it is possible to modify this correction in order to achieve exact regulation. And it is by now well known that in order for a controller to achieve exact regulation, it needs to have integral action. So it needs to implement a corrective action that is not just proportional to the error, but the integral of which is proportional to the error. So essentially, the controller needs to integrate the error so that as long as there is an error, the corrective action increases. And eventually, the system can settle only once the velocity error is exactly compensated. And you see that the device, this is sort of a schematic device of Jenkin's governor, that the main difference between Watt's governor and Jenkins' governor is that now you have two independent rotating devices. The one that has these fly balls very much like in Watt's governor, and then the one that will eventually dictate the corrective action. And in this case, the corrective action will be proportional to the angle, to the angular displacements of the second device. And you see that this second device will rotate as long as there is friction between these two, that is, as long as the velocity error is not exactly compensated. And in fact, so that's why yeah, I'm not sure I should. Yeah, that's why this device is sort of more complicated, because you have two independently rotating bodies, and it is through the friction between the two that you correct the velocity error. And in fact, most of the complications of the governor's designs in the 19th century were devoted to achieve integral action on top of proportional action. In fact, at the time of Maxwell, it was not even clear whether it would be possible to achieve exact speed regulation and stability together. And in that sense, Maxwell made a very important contribution. And in fact, this is still taught today, how to achieve integral control. I would say that a vast majority of controllers today in industry are designed just to achieve exact regulation through integral control. Okay, so why can we really think of Maxwell's paper as the first paper of control theory? Well, control theory is exactly about that. It's about theorizing stability analysis and integral control, and of course, further developments beyond these two notions. But this is the very first thing we teach today in a control engineering course. We teach that we can understand the stability of the feedback systems in most situations just through linearization. And as a second step, we teach that once we have achieved stability, the very next step to performance is to have what we call static performance, to reject perfectly uncertainty in steady state condition. More generally, control theory is really about theorizing the fundamental concept that feedback can compensate for uncertainty. And that concept is extremely widespread in all areas of engineering and, in fact, beyond engineering. Now, today, the modern form of integral control is far more sophisticated, eventually led to what we call the internal model principle of control theory, namely that a controller must possess a model of the disturbance to be able to compensate for it. And the simplest instance of that is that if a disturbance is constant, it can be modeled as a first-order differential equation, as an integrator, and therefore the controller must have an integrator to achieve integral control. Now, if you look at the history of control theory after Maxwell, well, probably the first next big step of control theory happened in the 30s through the invention of the feedback amplifiers and the developments of long-distance telecommunication that require to have very stable amplification through many amplifiers in cascade. That was called the repeater problem. That mostly occupied all engineers at Bell Labs in the 30s and 40s. And names like Nyquist and Bode essentially reduced this headache of designing these cascades of feedback amplifiers to the stability and performance analysis, to very elementary mathematical questions, very much in the same way as Maxwell did. Maxwell did it in what we call the time domain through differential equations, whereas Nyquist and Bode did it in the frequency domain. But fundamentally, they were also making use of elementary complex analysis to reduce complicated design questions to elementary mathematical questions. And then if you come closer to our time, you can see that control engineers today still contribute to identify principles like integral action, but perhaps in cells today. And I would say that the substrate of control theory doesn't really matter. It really depends on what is the important question at a particular time. Probably it was governors at the time of Maxwell, repeaters at the time of Nyquist and Bode, and probably today biology is a big area where people try to understand feedback mechanism and regulation principles. To conclude, I would say that Maxwell's science was probably the time of the formal detachment between what we would call pure science today and applied science, or mathematics and physics from engineering. Those two disciplines became more and more separated in the 20th century. But I don't think that Maxwell saw this as a hierarchy of nobility, that pure science would be more noble than engineering. Instead, when you read the papers on governors, it's very clear that Maxwell wants to emphasize that pure science must be eventually the method of engineering. And many engineers would say that, well, Maxwell's paper wasn't really a contribution to the field of designing governors. But instead, I think that what Maxwell did is to introduce principles, mathematical principles, in the analysis of governors, showing that eventually it is those principles that should govern the design of artificial devices. And I think that Wiener didn't choose randomly his reference when he wanted to choose a father to control theory. Wiener had an incredible culture. He was very versed in philosophy, art, and I think he chose Maxwell on purpose because he really wanted to acknowledge a scientist who valued the method of pure science as the preferred methodology of engineering. And I would say that this has been exactly the core principle of feedback science for the last 150 years. And beyond control theory, if you look at what is done today in engineering, it's very clear that physics and mathematics have become the core principles of making any significant advance in engineering. Thank you.
Thank you, Rodolphe. We have time for several questions. Any questions? First row, I'm sorry. Oh, we've got to get that. We're actually a minute or two early here. We'll get the microphones set up quickly here.
Can you hear me?
There you go.
Just to comment on your last slide, I think it's very important to emphasize that when Maxwell moved to Cambridge to form the Cavendish Laboratory, in the mind of Cavendish, William Cavendish, was that this was going to support British industry. It was the whole intention was to create a generation of new scientists who would make contributions across the whole of engineering as well.
Right.
Any other comments or questions? Second row, first seat here.
I'm wondering, what is the relationship between this internal model principle and what we would call machine learning?
Oh, I don't think there is much relationship. You know, feedback control is really about compensating for uncertainty. If you have a device that has no uncertainty, you don't need feedback. And so if you see where feedback survived the evolution, it's always in areas where there is a lot of uncertainty. Now, machine learning is about learning, adapting. And of course, feedback is central to adaptation. So there is a link between machine learning and regulation in this adaptation. But I wouldn't say that machine learning must compensate for uncertainty. Machine learning is sort of an automated way of learning a certain input-output rules, but not necessarily in the presence of uncertainty.
Yeah, it was somewhat rhetorical. So some of my machine learning colleagues, say from Carnegie Mellon, I think, I'm just spotting it and mentioning it, would sort of identify some of what you've described there as what they're encoding when they're developing their machine learning algorithms. They're actually embedding at the heart of it models.
Right. Now, you know, machine learning, of course, is tightly linked to biological learning. And there's a lot of interaction between how animals learn and how machine learns. And it is now by now well established that the way we learn about a lot of things is indeed by building an internal model of the environment. So in that sense, there is a connection. Yeah.
Interesting. Just a side comment, in my field of microwave engineering, topic has become popular called space mapping, which is similar to what you're just discussing here. Any other questions? We have time for several questions. In the very back there.
You talked quite a lot about stability and linearization. Is it the relationship between Maxwell and control theorists and control engineers? Is there some paternity perhaps to be ascribed to Maxwell in relation to nonlinear systems and nonlinear dynamics?
Well, I would say that the winning method of Maxwell was linearization, really. And stability at the time was very much understood as a nonlinear problem, hence this focus on energy methods that could account for nonlinearities. And in a sense, it was Maxwell's winning method to realize that you could make most of the predictions through linearization. And this is something that certainly has played a very fundamental role in control engineering, because many feedback systems are at first sight thought of as very nonlinear devices. And yet, when you talk about regulation, it's indeed true that a local analysis essentially based on linearization is often very successful.
Another question here about a third of the way back. Wait for the microphone, please. There we go.
I believe that the presence of nonlinearity usually has the potential for chaos. Was that ever mentioned at the time of Maxwell's attempt on these problems?
Oh, that's a good question. Well, I think that the turning point for the realization of chaos was the work of Poincaré. And Poincaré, if I'm not wrong, is 1877, so it's slightly after. And I'm not aware of Maxwell's ever commenting on even corresponding with, well, I think by that time he was probably dead. So I don't think that Poincaré and Maxwell never... Not that I am aware of, but it would be very interesting to see whether that happened. Yeah.
We have time for one more question. Sir Michael.
This is a comment about your reference to Maxwell's work on the stability of, depending on where the roots of polynomials were and so on. And also you referred to the difference between pure mathematics and applied mathematics. But the whole work, number theories, ever since that time, large area of it, are concerned exactly with this question about where the roots of polynomials lie, and all the big parts of number theory depend exactly on the same questions. And there's not a coincidence that the work of the pure mathematicians are doing and the work of the people who study methods of computation, which is what you're doing when you're more and more, they are the same. So the pure mathematics and the applied mathematics are not actually different. They are the same thing, and Maxwell knew that.
I very much agree, yeah. Even though the problem of determining the roots of a polynomial are in the left half plane is far easier than determining where the roots are, but yeah, definitely.
Thank you. Let's thank Rodolphe one more time.